thanking everybody for attending. I'm hoping that you'll enjoy the presentation and learn a lot from it, but also gather some questions to go off and do some more research of your own. So to get things started, I'll just let you know a little bit about me and a little bit about the paper that I'll be talking about today. My name is Jennifer Williams, and I am currently a firmware engineer PhD intern at Intel, working on next generation sensor networks. And I am also working on my PhD at Oregon State University, and I have just recently gotten to candidacy, so I'm working towards the final defense at this time. So what I'd like to share with you is a little bit of work towards that research in my PhD. And it goes to show just how important this research is around the world, both in academia and industry, and even getting into the consumer lives as well. So this talk today is enabling densely scalable, low power wireless sensor networks for shipping and industrial IoT. And this is a paper that was accepted and presented at IEEE's Ubiquitous Edge and Mobile Computing Conference at Columbia University just last month. And you can see there's quite a few contributors to this work, and actually there are more than just listed there as the authors on the paper, and we do have some acknowledgements at the end that we'll share with you as well. So if you want to follow up with anybody, or perhaps you recognize their work, that'd be great if you could reach out to them. So getting things going here, I'm going to start off with just kind of the topic of today with shipping and industrial IoT and the track and trace solutions that are out there, kind of motivating a new design and motivating us to challenge what's out there right now to address the trade-offs that we see in a lot of the design. So we'll start off by looking at the design and the framework to make the sensing and communication protocols happen. And we'll look at some of the physical components and the software to make the actual device work in the field. And then we can look at some preliminary results and go over a few remaining work ideas, and again, go over some of the references and affiliations for this work. So it may not need to be said, but it tends to help to look at where we're working as far as the design space goes. So this work spans many active research areas, and you could pick any one and dive into another dozen research areas within it. So it's a very broad topic, but it is also something that we need to be aware of what other research is going on in the field, whether it's directly related or a next step to be related to what we're working on. For example, if we start at the far left with wireless sensor networks, it's great for getting all of that local data, that local sensor readings from your different devices and getting it to a central hub. But then the next step would be connecting that hub out in the deployment space, connecting it to either a gateway or a sink to get it up and to get it up onto the internet, or to connect it over longer distances. So that's where we see the low rate wireless personal area network come in. And then once we start looking at extending that coverage even farther so that it's no longer just a personal area network of, we're looking at miles, kilometers, that kind of thing, we look at low power wide area networks. And those low power wide area networks are really where we start connecting to the Internet of Things. So we can actually reach the cloud, we can use some of the web services and get to the end user a lot more quickly that way. And so that is also branching off into industrial IoT, or what's also being recognized as the fourth industrial revolution, because we will see a very huge transformation in the industry and our lives as sensor networks and technology and cloud services all start to integrate with our lives in ways that we see and don't see. And so then the next piece is software-defined wireless networks, which is it's not a new paradigm. It's been around for a while, but it's starting to get a lot more attention now that we have more platforms and more ecosystems for IoT development. So there has been a lot more interest in exploring the possibilities with optimizing and minimizing power consumption for these low power sensor networks. So if we take a look at what this looks like as a system, then we see over on the left side, the low power wide area network, where we're connecting the personal and the local network over to a base station where we can connect to some and backhaul network and connecting that with the end user. So we see this already today. It's in existence, but what we're finding is a large amount of challenges happening at the edge. So while things are really taking off with web services and capabilities with analysis and forecasting, getting that data collected on the field at the edge is still a challenge for the resource limited devices. So I've got a bunch of the challenges for low rate wireless personal area networks down on the bottom part of this slide. And we don't have to go over all of them. I just wanted to show how many there are, and as you optimize on one, you may be affecting the performance of another. And so it's definitely this energy versus data trade-off that we see. If we try to get more data, we're going to use more power. If we try to communicate more frequently, we use more power. So there are trade-offs to whether we want high quality data or more data more frequently, or if we want to process anything on that data out on the edge. That is all very expensive for power. So what we're seeing in the literature, even just in 2016, the last year, was that to be realistically adopted at large scale, wireless sensor networks in industrial IoT specifically must still exhibit all of these characteristics, and they've not yet been completely met. And I wanted to take a moment to call out to one of the other talks that was happening in this conference. Just yesterday, it was by GB Raphael on towards zero delay shipping. I've got it written down here. I should find that, 1 second. But he was talking on industry pain points and how wireless sensor networks could address that. So I urge you to check out his talk yesterday. It should be recorded on the platform for you. But he talked a lot about how the existing technology out there cannot meet all of these characteristics in one go, and especially trying to make that happen across state lines, across entities, and across nations. It's very challenging to make one system widely applicable like that. So it's still a challenge, and it's still something that researchers are looking at in every country. They're looking at it in industry and academia, and there's even collaborative work to make this happen because it is such a complex challenge. So just to summarize here, the entire world is interested in finding a solution for track and trace devices, especially. So we can use those in shipping and industrial IoT. And GB goes over quite a few of the examples for that. So, and what the benefits could be. So that's not really part of this talk, but for, kind of a reference for you. You could go check that out. Alternative techniques. There are plenty of other existing technologies and new technologies coming out in the literature that are suggesting various platforms, whether that is the hardware or the software that is going on them. There's also different physical layer differences that you can, or different physical layer techniques that you can take to improve power and improve your connectivity and your quality of service, how much data you can get. But again, they're all trade-offs for energy versus data. So it's just it's a design challenge that there's no one great way or one correct way to design the system. So today, what we wanted to do was show you how theoretically we can go about a dynamic communication protocol that is scalable to a dense number, and also how you might construct the software to make that happen. And then also the reference hardware that can actually run that suite of software. And the hardware that is highlighted here is meant to be as small a form factor and ultra low power, ultra low duty cycle. So what we are trying to accomplish here is the latest solution in low power wireless sensor networks. So for this design strategy, to make this system actually work, we're looking at using IEEE 802.15.4, which provides definition for the physical and MAC layers, and we're going to be working on the 2.4 gigahertz spectrum. So 15.4 provides a scalable topology that starts with the star topology or the star architecture, and that's what I have shown here on the slide. So you see that there's a central node that is directly connected to each of the children nodes. And what we have in this particular diagram is labeling them as the clients are the edge nodes, or the children, and then the server is the central PAN coordinator, or the personal area network coordinator. And that server is connected to the gateway device or component. So that gateway at the very top of this star is what's assumed to have a wider area connection. So whether that's 3G or Wi-Fi or something like that. And then it's a physical connection, just a serial connection between the gateway and server for their communication, just transfer of data and commands. And then the server to clients is a wireless connection using the 15.4 protocol. And the way that this design goes about controlling channel access is to say that each personal area network or sensor network is going to use one channel. So they'll share the channel. And this is also what's called a many-to-one channel. And it is a very common approach in densely scalable networks. So there are 16 channels available on the 2.4 gigahertz spectrum. And so each PAN would be assigned one channel. And on that channel, if you take the time that we want to report, you can divide that time period into equal divisions, and we'll have one that's specific for the beacon coming down from the server. And that's just a message that's communicating very basic commands, and at minimum, it's providing just a temporal reference point for the client nodes. The way that the clients are synchronizing on this network and behaving on these time slots really depends on their time synchronization. They have to be synced up, so to speak, or at least referring to the same timing reference point so that they can know when to wake up and receive the beacon that's coming in. And also a reason for this timing structure is because these client nodes are going to need to go to sleep as much as possible. So the timing has to be very specific so that the clients can go to sleep for a precise amount of time, wake up at just the moment when they need to for the beacon to come in, and then they'll go to sleep again. Now, these are sensor nodes, so that does mean that they will need to also wake up to collect their sensor data from their own sensors and package that into a message and send that upstream themselves to the server. So that's what this diagram is showing here beneath the star topology, is that we have the server sending a beacon down during its time slot, and then the clients are sending their messages or sensor data back up in their assigned slot. And then the last little note on this slide is that we wanted to show you that many of the low power microcontrollers available are coming out with energy levels that are available to shut down various parts of the hardware to reduce power consumption. And you can do that at different levels, whether it's a moderate shutdown of the hardware, so it's more like you've just shut off some of the access to like the transceiver or something like that, then that brings it down a bit. But if you want to really shut down everything, like shut off access to a bunch of the ports, then you can put it into the sleep or idle modes, and those are much lower. And so to give a little more insight on what the device types are and how these are behaving on the network, and also looking at the messages that are flowing on the wireless channel, that's what this slide is taking a look at. So we do have the clients, and these are, according to the 15.4 spec, a reduced function device, and the servers are 15.4 full function device. And the difference is that the full function device is capable of being the PAN coordinator. So that's the distinction there, and tying it back to the spec. And then so you see on the right-hand side, I have a general graph of what this behavior would look like for a typical, what we're calling a microframe. And the microframe is really just a minimal period of reporting. So in this particular example, we're saying that it's a 60-second reporting structure. So every 60 seconds, we expect to see a beacon come in at the beginning, and then messages from the clients flowing upstream thereafter for the whole minute. And then it would just repeat the cycle. And that provides an opportunity for not just the beacon to go down and synchronize every minute, but also for the clients to have every minute an opportunity to say that there was a sensor reading above threshold, or even to just provide all of the sensor readings so you can put together some kind of trend analysis or something like that higher up in the chain for the IoT. So what we see on the right there is, on the top row is the server, and that's its behavior on the transceiver. So it transmits a beacon, and then it receives the client messages. And now these are all kind of like a timeline from left to right. So on the next row is the client in that same timeline. It's going to wake up early to pull for sensor data so it can get its message ready. It'll be awake to receive that beacon coming in, and then it will send up its message. And that is client 1, so it'll use the first time slot that's available. And the second client down below it is going to, very similarly, wake up to pull sensor data and receive the beacon. It is assigned the second time slot, so it goes to sleep during the first one, so that client 1 can actually transmit its message without any traffic on the network. And then there's client 2 would wake up in the second time slot to send its sensor data. And so something else I'll point out here is that on client 2, you can see that the pull sensor data and receive beacon periods are shifted to the right just a bit. And that's just to simulate or to show you that part of what this design incorporates is a beacon listening phase, because there could be a drift in the local clock on each of the devices. So each device is relying on timers and counters to govern its operation, when it wakes up to pull for its data, when it receives the beacon, and when it transmits its information. And the server is also depending on that local clock of its own for doing all of the transmitting beacons and receiving messages. So, but what we see is that each of these local clocks has its own behavior, unpredictable behavior of the local crystal oscillator, and it depends on how good the oscillator is. And but that's also a design trade-off, because if you get a higher quality oscillator which will exhibit less drift and give you a more accurate clock over time, it's more expensive. And all of these devices have to be kept at a very low cost, almost disposable cost, so to speak. So that's not an option. So we have to build a way to handle if you use a non-ideal oscillator. So for instance, perhaps one that's built into the part, or you could choose to use one that's less perfect at the expense of needing a beacon listening phase. So the blue box, that's the receive beacon box, that's that listening phase. So the transceiver or the receiver has to be on and receiving for an extended period of time, a guard band before and after the expected time of the beacon, just in case the client or the server drifted temporarily on its clock. They could miss each other. So that's what that guard band is. So getting into the hardware and testbed just a bit, this is just a highlight of the components that were used to test out the software design and the protocol design. So what we see here is that we have the actual component name on the left, and these are all commercial off-the-shelf components. And we wanted to make sure that it was all commercial off-the-shelf components to make sure that this would be something that could take flight quickly and also be something that was familiar with the industry. So we see the first item is the microcontroller evaluation board, and that is the larger board that you see in both of these pictures here. And this is an evaluation board. So ideally, once this goes towards actual deployment, whomever's designing this would want to make sure that it's as small a form factor as possible. So some of the headers and some of the extra components could be removed to make this much smaller. So that's why it does appear a bit large, is that it's an evaluation board. So things are more spaced out and available for testing and inspection. So then you also have the light sensor evaluation board, and that's the smaller board on the left. So we have the single sensor client is in the figure labeled A, and that is the small board that I'm talking about with the light sensor evaluation. So that is just connected by I2C and collecting ambient light data. And again, that one is an evaluation board too, so that's much larger than the actual light sensor is. And the humidity temperature evaluation board, so humidity and temperature are actually built into the microcontroller evaluation board in this picture, but there's also humidity, temperature, and pressure sensors that can be run with this sensor network as well, and those parts are listed. And then, of course, coin cell batteries, and there's a programmer board that's required to just flash these boards with the software, but they're not required during deployment. So, but it is listed as some of the hardware. And then this piece on the right of the figure B is the adapter to what we're calling a gateway simulator. So again, this wireless sensor network is intended to be physically connected by serial to, or serially connected to a gateway component, which would give us more capability and more processing and connectivity, perhaps a wide area connection or something greater like that. So that's all that piece is to signify, is just allowing our serial connection to go off to the gateway. So what we're asking with this testbed is, can several nodes work on this network, and can it scale up densely? And then can the network survive greater than 15 days? 15 days was a minimum, but it does depend on the use case. It vastly depends on the use case, even within shipping and industrial IoT. There are some the track and trace solutions that would require only a few days, but maybe you need reports every 10 seconds. So it would eat up your battery, or perhaps there's another deployment that requires several months or years of track and trace. So anything could happen with the design once you start considering the use case. But for this particular one, we identified at least 15 days reporting minute to minute of sensor data, or anomalies as we call it, or anomalies is a sensor reading out of threshold, something that is indicating a sensor reading may be wrong or maybe off, or something needs to be checked with the track and trace. And so the software discussion is, excuse me, just to kind of overview what the protocol architecture looks like and how we are leveraging the current standards of 15.4, and how you might actually be able to include an application that might use this data to do something else. For instance, if we look at the left-hand side, then we see 15.4 provides the physical and MAC layers, and then there's the wireless sensor network that we're offering here. And then the application might actually take that sensor reading and say, now I need to turn on this motor, because like perhaps you're working on an irrigation system for agriculture and the soil moisture is getting a reading that's too low. So then it might turn on a motor to turn on the water pump and get some things going there. So in that sense, it it's a scalable architecture and it's dynamic for many applications. And then if we look more deeply into the software architecture there in the middle of the slide, then we can look at what the upper layers and the high MAC is, what is composed there. And so we see the wireless sensor network modules that can be broken down into a main one that will call out to a common file that is, and these descriptions are also better detailed in the paper. We don't have a ton of time to go through everything, but we'll touch on what we can. So also in the common module, that will contain things for like getting sensor readings or sending out data and things like that. And then there's a module for whether it is a server or a client. They both have their own behaviors, and that should be apparent from the protocol, where the server is sending out beacons and is responsible for its children as a PAN coordinator. And then the clients are actually doing behaviors that are a bit more headless. They want to go and just read their sensor data and transmit it up, and they're not responsible for the health of the network or anything along those lines. And then the sensor module is very specifically to contain the functions for pulling sensor data from the various sensor modules that you might have on the board, like pressure, temperature, humidity, that kind of thing. And then we have the low-level firmware and the hardware abstraction layer that allows us to hook into some of the BSP and the MAC layers below. And so as part of the low-level MAC, 802.15.4 provides the headers and the mechanisms for accessing the channel and controlling the network behavior. And then the physical layer is getting us down into working on the 2.4 gigahertz and our radio components, the timers and drivers, and helps us to identify things like what frequency, what modulation scheme, what particular hardware are we running at this time, things like that. And then the upper layers are mostly inspired by the software-defined network paradigm that I mentioned earlier, where we start to say what is a temperature sensor and what is too cold and what do I need to do about it. That's where we start answering some of those questions. And so here, if we start looking at some of the results, then what we see is that we started off with the association beacon, and we wanted to make sure that the reason for this association beacon is to allow this brand new network a way to form, to associate with each other. Because at first, the server and clients, let's assume that they have been told which channel to talk on, and the clients know which gateway to talk to, but they don't know their time slot. They don't know when to talk, and they're all being powered on at a different time. So their reference points are not aligned. So the first thing that has to happen is the server needs to be on and transmitting out a fairly rapid beacon. And that's the association beacon that I've shown here, where it's a very basic frame structure. We have a command byte that tells us it's this association beacon type. And then there's the bitmap of the time division assignments. So I'll allow you guys to take a look at the paper and kind of look into how we're doing that assignment. But basically, the clients will scroll through that bitmap of TDM data, and they'll find their client ID, and whatever index that is, they will use that index as theirs for the rest of the session. So what that means, if we look at the graph below it, is that on the top line there, that's the server transmitting the beacon. We can see two clients below that are waking up to receive with their listening phase. And as soon as they receive the beacon, they go to sleep and they wait for a governed period of time. And then this second client that's shown there is client number 2 and 3. So we're seeing transmits in the second and third slot there. And then, so what we see from that graph is that now the clients have received the temporal reference point from the beacon. They have responded in their appropriate time slots, and we're now an organized network, something that is working according to the TDM, and we are deterministic at this point. It's no longer a chaotic network. So now we're in what we're calling a managed mode. And so we see this just managed mode beacon. There are a few other kinds of beacons that can come through, but that's just up to implementation and what you need to happen. But the main idea is that this regular beacon is coming in with a minimum payload just to say that this is the temporal point that they need to reference for the time synchronization of the TDM network. So in the managed mode graph over here, we see this server non-idle powers on the top line. So that just shows you the server is asleep until it turns on to receive everything. And we see this on the next line, the server receives signal. So that allows you to see that it is receiving from the various clients that are connected to it. And I apologize, the next trace was an error. There was no trace for client 1, but we see client 2 through 6 on their transceive lines down below. So you can see there are various wake up times for the beacon. And as soon as they receive the beacon, they go to sleep and they wake up to transmit in their associated time slot. And it's a nice cascade and helps to control the channel occupancy. So you can see that we've designed this many to one channel here. And this is another look at the actual behavior at the client itself, and also a bit of a look at the server. So the assumption is that these devices or the sensor network will be in association mode for only a brief time, maybe a few minutes, maybe up to an hour. It's up to the design. But the idea is that the sensor network will spend most of its time in that managed mode. And so they know exactly who they're talking to, they know when to talk, and they know to go and pull their sensor data and report it up. And we're just in that very governed mode there. So what we see is this client current consumption profile, and you can see in the table here that we've separated out the different activities. So there's deep sleep for the clients. There's deep sleep, listen for beacon, send message, and collect or pull the sensor data. And those are also identified in the current consumption profile, which is in the middle there. So deep sleep is the lowest current consumption. And then after we wake up, then that's listening for the beacon. And you can see that this is where we are using the highest percentage of our current consumption. So this is the most power hungry state, is using the transceiver. So that is something to take away from this study and looking at the current profiles. And it's the next step of optimization, is trying to get even further to an ultra low duty cycle. But what we do see is that listening phase here for the beacon, and then also at point C is a quick burst of the sensor data, and then D is where we're pulling the data. Now this pulling the data can either happen, it depends on implementation, but it could occur before it listens for the beacon, or before it transmits the sensor data, or after, like you see here in this plot. So in this particular implementation, it was done, the sensor readings were collected after sending the report. Then so I guess let me just highlight one last thing with the client current consumption would be that we are spending 99.9% of our time in deep sleep, even in this current consumption. So it's interesting to see that even though it's such a high number of being in deep sleep, we still need to optimize in a couple of places, like listening for the beacon and even transmitting the data. So there are a few places where we can improve here and reduce the duty cycle and improve the lifespan. But even for what we have provided here, It definitely meets the design requirements, and lifespan experiment validates the low power design. On the right-hand side, the graph is showing for an accelerated reporting schedule. So even though this is only going to 10 days, these nodes were actually reporting at, I'll have to actually look at the paper. I can't remember what the rate was, but it was, I believe, every 30 seconds reporting instead of every 60 seconds. So at minimum, this would be a double, or this is twice the consumption rate. So what we're seeing at the end of all of this is that we're trying, the world is trying to solve the problem of building this large-scale wireless sensor network for applications that are exhibiting gating requirements, such as those we see in logistics and asset management in industrial IoT. And we also see a lot of designs that are leveraging available standards and low-power components and energy-efficient techniques. And something that's even taking more interest lately is software-defined wireless networks and their capability of offering flexibility and a framework for customization and optimization. And so what we did today was explore a dynamic wireless sensor network protocol that can be largely scaled and does leverage available protocols or available standards, and also uses available hardware to provide a solution that could hook into something much bigger. And there's also software framework and development that we covered here. So there's a suite of resources to enable a wireless sensor network that is largely scalable for shipping and industrial IoT. And so I'd just like to take a moment to provide some acknowledgments to our special colleagues that helped make this happen. Got all of the authors and their affiliations listed here. You can see that this was collaborative work between Oregon State University and Universidad de Cauca in Colombia and Intel Corporation. And we had several colleagues that were working with us all along the way, from use case to cloud interconnections and architecture and sensor modules and all kinds of things that they've been helping us with all along the way. So we like to reach out to them. And these are the references, again, just highlighted from the paper. So feel free to check those out. Really great stuff out there. And I just wanted to say thank you and open the floor for some questions and see if there's anything I can help clarify for you. Thank you very much for your time. All right, I have a question. Any solution for difficulties in developing a business which embraces the full potential of Internet of Things? So I guess I'm having a little trouble understanding what the question would be, but there are certainly difficulties in creating a business to embrace all of the Internet of Things, because there are so many different aspects to the Internet of Things, whether it's the hardware or the software, or it's the actual deployment or the maintenance or the artificial intelligence and the learning and web services that can happen. So I guess the solution would be to recognize the enormity of the situation and how there are going to be a lot of experts. Oh, for the clarification. So difficulties in developing a clear approach for enabling innovation, trust, and ownership of data in the IoT, while at the same time respecting security and privacy in a complex environment. Absolutely. So there are a world of difficulties with that. It's fascinating to see all of the startups and security-related companies that are popping up around technology and IoT. And it's interesting to see it's gotten more attention in the last year or so. But it does seem like certain companies are taking very specific approaches. So they're trying to solve one problem. So I can't say that I know of any that are really going for the full potential of Internet of Things right off the top of my head, but I can imagine that there's probably very few that can solve all of the problems for IoT and offer security, but it's something that we're all striving for as developers, and consumers are trying to find it, and as just developers, we're trying to better the world and make it more secure and more affordable. So I'm not sure if that answers your question. I got a question here. I'll read it out first. A ballpark estimate for time to market as a commercial product based on the 15.4 standard. So I actually don't know the answer to that one. I have most recently been focused on a research aspect of it, so I'm not familiar what the timelines are with the time to market for it. But I know that as things like Zigbee and 6LoWPAN and other newer platform or newer protocols are released, and the more they're used out in the field, the faster we'll see that time to market go up. So I think that, like it will take less time to get things out as more people become more familiar and as more platforms become multi-standard. So hopefully we can improve that time to market, but I don't have an answer for you. I have a comment here. The absence of standard procedure leads to the even greater challenge to practice, thus adding question mark to its value. Yes, agreed. So, and then there's also a challenge in the various standards that there are, and it's a whole stack. You know, when we look at the hardware and the software, and we look at different design decisions throughout, we see that there are standards for the serial communication. There are standards for some of the algorithms. There are standards for how you do the watchdog for some of your wake-up timers. And then we see standards for 15.4, which allows you to leverage certain things and then build above it. So then we start seeing a lot of that. And I have another question or follow-up here. Is there any procedure to practice IoT in real time? So there are a lot of applications that will use real-time processing and real-time feed for IoT. In this particular design, we're really providing a means to report sensor values or sensor readings at a scalable granularity. So although our example was for 60 seconds, you could make that every 10 seconds or something if you wanted. Just might have an effect on the scalability of the network and might require some other mechanisms to handle that. But as far as getting things in real time, systems are meant to report based on the last minute or the last 10 seconds. But you could, like I said in the activity profile that we were looking at, if you play with where you pull your sensor data, you could work towards getting a real-time IoT. So you could you could pull the sensor data just before you send the message, and that way you're sending the latest data. Sabarana says, I am from India, undergoing deep research to apply advanced technology for smart farming, digital marketing, arts and crafts, and a number of things. That's excellent work, yes. Seeking advice regarding Intel products for IoT. Well, then this is I'm glad you found this conference. I hope you're finding a lot here to help you. Between yesterday and today, there have been some really great talks and really great topics. So he's saying, spending a lot of time prototyping projects, okay. Question is, any standard operating procedure for designing IoT to transform traditional into smart in each and every sectors? Has this technique been used in real world? So yes, we've had some preliminary success with this specific protocol, but we know from practice that this hardware and the approach and the TDM process, the sensing algorithms and even the 15.4 protocol or the standard there, that all works, and that's all been tested in the real world. So it should be very straightforward to start moving this forward and into some more studies and comparing the architecture and comparing the behavior and the power consumption with what's out there, and start really getting it out into the real world. So, but if I start kind of coming back to Sabrinath's question there about any standard operating procedure for designing IoT, I think that it is it's something that takes time and experience, and just I don't think there's any like one go-to book that anybody says is, you know, the manual for IoT development. But it's really a matter of best practices and becoming familiar with the field, and recognizing the challenges that are faced in every single design approach, and kind of looking at a magnanimous approach to it, looking at not just what you are designing, but how that will influence the next stage in the design, or the next use case, things like that. So it's great that I see, Sabinath, that you're getting into some of the security and something that is a complete solution. So there are some places out there, or some companies out there, that are really looking into security and public sector, and how to protect our data and our devices. So it just kind of depends on where you're trying to design and where you're trying to kind of leverage with other experts. We have a question from Dave. What was the greatest technical challenge in creating the PC prototype boards demoed and results they're based upon? Okay, so one of the greatest challenge, oh wow, that's always a tricky one, right? That is a curious question. But I guess one of the greatest challenges was, well, for me, I'm working on it from a system architect and a firmware engineer standpoint. So it was really interesting to work with the sensors themselves. So working with the sensor drivers and trying to get the configurations right on all of the sensors, so that we were getting the low power measurements that we wanted, and making sure that we were setting for one-shot measurements from the sensors instead of continuous polling. That way we could save a lot of energy. And the accelerometer was certainly something that gave us a couple of new challenges and made us scratch for some of the algorithms. It's a learning experience that I didn't expect, but I'm really glad that I got it. So yeah, I guess integration of the various sensors. So it's a buzzword, sensor fusion, right? So that was a good one. So we've got another question from Sabrinath. As awareness grows, the adoption rate is likely to increase for IoT that will automate business operations and end-to-end processes. IoT has advanced exponentially beyond to achieve greater and greater possibilities in small-scale industry to work smarter. Yes, it's fascinating. We've had some presentations about that too with this conference. So I hope you can check those out. And Sabrinath's posting some more about small-scale industry and how it can create added value for customers and innovation and data-driven services. For example, a remote monitoring application allows small-scale experts to support customers from anywhere in the world, and they can also increase productivity. We do see a lot of that happening. I know over the last several years, there's been studies for especially agricultural, whether it's deploying these for huge crops that they need to monitor several different crops and year-round, different temperature, different weather, different climates, and then also things like vineyards, and there's even been things out for monitoring the quality of wine in the bottle itself. So we're starting to see things move from just monitoring large outdoor spaces or even in a greenhouse and doing smart greenhouses, but also going to the, once you've actually made the product and you're wanting to keep track of how the quality is while you store it for several years thereafter, and that's starting to be a big thing too. So those small scale industries. And from regarding power consumption, sensor power consumption. Good pun. Yes, it's a good point. Makes sense. Do you foresee recommended sensors as being part of the commercial solution versus sensors available on the open market? Well, with the approach that I talked about, modularizing the sensor network software stack, then you're creating a way that you could hook into the other drivers. So I mentioned the hardware abstraction layer, or the HAL, and that's a good way for us to just have our own functions that we're writing into the framework in this design and hook into a function that we know should exist in drivers. So for instance, the commercial off-the-shelf parts that I mentioned where today, like the pressure sensor and the light sensor, all of those. The manufacturer provides the sensor drivers for each of those units. So all that I needed to do was go in and take a look at what their functions were and start hooking into that. So theoretically, since we with one set of commercial off-the-shelf parts, and we have those as our known recommended sensors, you could step away and go for something else that does exist on the open market as well, and make that same hook into their drivers. So using the firmware level, you can actually kind of move around and play with different sensors, or a new lower power sensor comes out next year, you could swap this out and change much in the firmware, then you wouldn't even have to change that either. So it just depends, but certainly these are the recommended solutions, but that's just because we needed something to test with right away, but we can certainly play around with others. I know I've personally tested with this with a different humidity temperature sensor, new driver set, and it worked. So theoretically, any of the sensors available on the market, if they have a manufacturer supplied driver, should be able to hook in. And that's actually a really interesting thing, is that, and it was in GB's presentation as well, is that sensor power consumption has gone down drastically over the last several years. So it's making a lot more possible with a lot of our IoT designs and applications. And so even though some of the topics that you might hear about with IoT may be older topics that have been around for a while, they might be getting new attention because of the new sensors that are available. So new lower power consumption, new form factor, new capability to survive different shock, going underwater for some things. There are so many applications for these. Thank you, everyone. I really appreciate your time, and I wish you the best on your endeavors. Have fun with IoT.